Hello guys, in this video lecture we will study some properties of Hilbert adjoint operators corresponding to linear operators, bounded linear operators defined on Hilbert spaces. As you see, I have written some properties on screen, although there are other properties as well, but these are some important properties. We have a linear bounded operator T from Hilbert space H1 into H2 and another linear bounded operator S from H1 into H2, and the first property is about T star. That is, we can simply move T star from first variable or first coordinate into second by simply removing it a star. Second property is about the sum of the bounded linear operators, about the adjoint of the sum of the bounded linear operators, which simply states that if we have to find the sum of the adjoint of the sum of the two bounded linear operators, you simply find the adjoint operator of S and adjoint operator of T, then simply sum them by pointwise. And third one is about if we take the adjoint operator of adjoint, which simply states it coincide with the T. And third one is about the composition. If we have to determine the adjoint of the composition of two bounded linear operators, it simply states that you simply take the adjoint of S and T, then compose them individually. These are the four properties which we will prove, and we will provide some examples of the Hilbert adjoint operators defined on some Hilbert spaces. Before proving these statements, let me prove a theorem first, or a lemma we can say. Let me prove first a lemma about the zero operator on inner product spaces. Let us prove first, because we will need this lemma in proving these properties, which simply states that if we have a Q bounded linear operator defined on a Hilbert spaces X and Y, it is a lemma about zero operator. Let me write it here. It states the characterizing property of a zero operator. That is, it states that Q is zero operator if and only if. That it is the characterizing property of zero operator. That is, Q is a zero operator if and only if inner product of Qx with Y, where X and Y are the elements of X and Y inner product spaces respectively, is 0 for all xy belonging to X and Y respectively. So let us suppose first that this is a zero operator on X, that is, it is null space is whole of X, which we will prove this holds. Then we will assume this inner product holds, and we will prove it is a zero operator. So let us first assume that it is a zero operator. By zero operator we mean it is null space is whole of X, which implies Q of X is 0, 0 vector of Y for all X in our inner product space X. Well, now we will calculate inner product of Qx with Y, which is simply inner product of 0 vector with Y, which we can simply write as 0 scalar times some vector V in our X inner product space with Y. Since inner product is linear, we can bring out the scalar 0 inner product Y, which is simply 0, because any field number or any element in the field, underlying field, multiplied by 0 is simply 0, which implies that inner product of Qx with Y is simply 0. Now we will assume that this condition holds, and then we will prove Q must be a, if this condition holds for all X and Y, then this operator must be 0. Now we will assume that inner product of Qx with Y is simply 0 for all xy in X and Y respectively. We have to prove that Q is a zero operator. That is, we have to prove Qx is 0 for all X in our inner product space X. Since this holds for all X and Y in Y, it must also hold for y is equal to qx, because it is also an element of y inner product space. Hence inner product of qx with qx should also be 0. As you know, inner product of an element with itself simply gives the norm of qx square, which simply implies qx must be 0 by the property of the norm for all x in our space x, which implies simply q is a 0 operator. This is a simple lemma about 0 operator. Now let us prove our properties first. Then we will provide some examples of Hilbert adjoint operators. So let us prove our first property, which was about inner product of t star y with x is same as inner product of y with tx. You should distinguish between the defining relation of the adjoint operator and this equality. The defining relation for our operator, adjoint operator, was that tx, inner product of tx with y, must be same as inner product of x with t star y. Now here this is clearly a different equality, although it looks same, but it is clearly different. Here we are taking inner product of tx with the y, but here we are taking inner product of y with the tx, and here we are taking inner product of x with t star y, and here we are taking inner product of t star y with x. So these are clearly different notions. Once we will prove this property, then we can simply move t star from one variable, one coordinate, into second by removing it as star. Then we will, these two properties will allow us to move from one property into the other. So let us prove our first property, t star y x, which is simply, if I simply conjugate it by the property of the inner product, it will give me x with t star y conjugate. I simply interchanged these two, then our inner product will get changed by the conjugate. Now by this property, by the second property here, by this property, t star inner product of x with t star y should be same as inner product of tx with the y, which is, this should be same as inner product of tx with the y conjugated, which is same as, if I simply remove the conjugate, it will simply give us y with the tx. Hence our property holds, that is, inner product of t star y with x is same as inner product of y with tx. Now we can freely move from one variable into second by removing star and by adding star. This was our first property. Next property we will prove about the sum of the two. Next property is about the adjoint of the sum of two operators. That is, we have to determine the adjoint of sum of the two operators, which simply states that you take the adjoint of the first operator and adjoint of the second operator, then simply sum them pointwise. We have to prove this property. Now from the above previous from the previous property, we have, or we can simply write defining property of s plus t star. We can simply write inner product of s plus t of x with the y, it must be same as inner product of x with s plus t star by the very defining property of, because s plus t star is the adjoint operator corresponding to the sum of two linear operators. As we know, the sum of two linear operators is a linear operator, and a sum of two bounded linear operators is also a bounded linear operator. Therefore this is the adjoint of the corresponding sum operator. Now we know that inner product is simply linear in first, and s plus t is defined point wise. Therefore we can use simply point wise addition and the linearity property. I am using both ones. Therefore this leads us to this, which should be same as this. Now we can individually sum them, or we can from this equality we can simply transfer s into second by taking star of it, because s star will be the adjoint operator corresponding to s. That is, this will be equal to inner product of x with s star y plus inner product of x with t star y, which must be same, which must be equal to this. Now we can simply sum these two, x with s star y plus t star y, which is equal to this. Now let me rub it until we got here x inner product with s star y plus t star y is x inner product with s plus t star y. Now we know that s and s star and t star are both linear. Then we can again use the definition of addition, which is simply s star plus t star of y, which is same as s plus t. From this you simply get, from this by using the previous lemma, you simply get s plus t star of y is same as s star plus t star of y for all y in our Hilbert space, which implies simply s plus t star is same as s star plus t star, which proves our second property about the Hilbert adjoint operator. Now we can, it is simply defined for the two, but we can simply extend it up to finite number of linear operators. That is, if we simply have t1, t2, t3, tn, n linear operators, and we have to define the adjoint of these all, sum of all these, then it is simply t1 star plus t2 star plus dash dash plus tn star. It is about the sum. Now let us prove another property, that is t star star is same as t. So now let us first define the defining relation of our operators. Now we know that corresponding to our linear or bounded operator t, the defining relation for the adjoint was txy should be same as inner product of tx with the t star y. Now corresponding to t star, we know, we also proved that t star exists and it is uniqueness. Also we proved that this is linear and bounded. Now corresponding to this, we can define its adjoint, which is simply stated as t star, represented as t star star, or you can simply represent this by t double star, t star star. Now this is also a linear bounded operator, and corresponding to this we can define its adjoint. The defining relation for that operator must be t star x y should be same as inner product of x with t star star y. Now we have to prove that t star star is same as t. We will use the previous property which we defined, first one, and we will use it to prove this. Now let us prove this, that is inner product of t star star x with the y is simply as, which is simply same as inner product of x with t star y by the first property, and by the adjoint operator of the t, this can simply be written as tx with y, and from this it follows that t star minus t must be 0, because we already proved the defining property for the 0 operator. Q inner product with y is 0. If we have this for all x and y, then Q must be a 0 operator, which implies simply from this inequality t star minus t must be a 0 operator. Hence t star must be same as t. We simply proves our properties. Our this property t star is simply t. Now we will prove our property for about composition, that is s t star is simply t star s star. Since our s was defined from h1 into h2 and t was defined from h1 into h2, therefore st will be defined from h1 into st will be an operator from h1 into h1. st will be an operator from, this should be from h2, s should be from h2 into h1. This should be from, for this property s should be defined from h2 into h1, otherwise it won't hold. Therefore s will go from h1 into h2, t will go from h1 into h2 and s will go from h2 into h1. Therefore st will go from h1 into h1. Hence, in order to prove this property, we will also use our defining relation for the adjoint operator, that is inner product of x st star y is same as stx y, which is same as, by moving this s, we can see this first coordinate as s acting on tx. We can simply move s from first into the second variable, which will simply give us tx s star y, and now t, for t we can simply write this as t star s star y, and from this equality we get, that is we got x t s star y is same as inner product of x with s star t star y. Hence we got inner product adjoint of t s should be same as adjoint of t. This is same like if you what you have done in matrices, that is a b transpose is same as b transpose a transpose, because in case of the real matrices adjointness corresponds to simply transpose, which is the same property here, which we have already studied. Now let us provide some examples of Hilbert adjoint operator. So first example, now let us provide some examples. First let us define an operator t on LP into LP, where LP is the set of sequences which are p-summable. LP is the set of sequences set of sequences which are p summable, p summable simply means you simply take their components xi and mod them and take their pth power individually and then sum them from 1 to infinity. This should be finite. This is the definition of p summable. And for this we will define a linear operator and we will compute it as adjoint. Let us define. Now t will simply take sequences here and it will output sequences here. It will take sequence here and it will output a sequence. Let us define this by t of, let us denote our sequence element as by xk. This is our sequence. T takes this sequence and simply maps it to another sequence which is simply defined by xk plus 1, where k goes from 1 to infinity. That is, it takes this sequence and simply maps it to this sequence. Now it is clear that this is a linear operator. You can prove that. We will simply compute it as adjoint by the defining relation. And you should know how inner product is defined on LP spaces. Inner product on LP spaces simply defined by, let me first define inner product on these and then we will compute it as adjoint. Inner product on LP space is simply defined if we take two elements x and y. X will be a sequence and y another vector which will be a sequence. Inner product of x with y is simply defined by inner product of this sequence with inner product of yk, which is simply defined by summation xk yk conjugate k going from 1 to infinity. This is the inner product defined on LP spaces. Now let us calculate the adjoint of this operator. So our operator, let me write its definition here. T of xk was simply defined by xk plus 1. So by the defining relation for the adjointness, let us calculate first inner product of tx with y, which should be same as inner product of x t star y. We will simply calculate t inner product of tx with y and we will try to compare that inner product with this. From that we will simply try to explicitly define t star y. Now for this equality, it will be simply inner product of xk plus 1 with inner product of yk, which will be simply inner product of summation of xk plus 1 yk conjugate, k goes from 1 to infinity. Let us decompose this sum. What is this sum actually? So first term will be x1 plus x2 y1 conjugate. Then if we take k equals 2, then this will be x2 plus x3 y2 conjugate plus dash dash dash. This sum will be like this. Now we will try to decompose this sum in terms of inner product of x with t star y, which will simply give us explicit relation for the t star y. So let us decompose this sum. That is, until we got here, we have inner product of tx with y is simply x1 plus x2 y1 conjugate plus x2 plus x3 y2 conjugate plus dash dash dash, which is simply x1 y1 conjugate plus x2 will get common here and we will remain with y1 plus y2 conjugate, and then we will get x3 y2 conjugate plus y3 conjugate plus dash dash dash, which is exactly the inner product of x with which should be same as inner product of x with t star y. Now if you compare these two equalities, this suggests that t star y should be simply this thing, that is t star y should be simply this quantity, this sequence, it should be y1 plus y2 plus y3 dash dash dash. It should be simply this sequence. T star y should be like this, because now if you will take inner product of x with t star y, you will get the same equality. Hence t star y is defined y1 plus y2 plus y3 dash 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 dash. Let me give you another example of this adjoint operator, which we will compute for the right shift operator. We'll compute adjoint of right shift operator. Right shift operator is simply defined by, it simply takes a vector or a sequence and simply shifts it by right by 1. That is, we have a, but let us suppose we have a Hilbert separable Hilbert space here. We will assume that we have a separable Hilbert space, and let us suppose En is our total orthonormal sequence, which is possible. That is why we are taking separable Hilbert space, total orthonormal sequence. And let us define an operator T from H into H. By simply it takes the nth vector in this total orthonormal sequence, it takes the nth vector, it simply outputs the shifted version of it. That is simply, let me show you example, like if it takes a sequence 1 0 0 dash dash, it will simply output E2. This was our E1, it will simply output E2, that is E2 is simply 0 1, that is it simply shifts this by 1. Therefore, like if you take another example like 0 1 0 0 0, it will simply shift this by 1 unit, so we will get this 0 0 here. Now let us try to compute adjoint of this operator. Since we can take any vector here x and try to decompose it in terms of this orthonormal sequence, because this is total orthonormal sequence and it is shorter basis for our Hilbert space, and we can write any vector here x in Hilbert space as as a series of Ens. That is, we can simply, if we take any, let me write it here, if we take any vector here x belongs to H, we can simply write this vector as summation of alpha I ei, where alpha I are scalars from the underlying field. Now we will try to obtain image of this Tx first, then we will try to compute its adjoint. So let us first define Tx. Tx will be simply summation alpha I ei, 1 goes to infinity. Now we can bring, we can first, since T is a bounded linear operator, so we can simply use we can first change this into limit and bring it out and take the finite sum out, because this is linear operator, which will be simply, we can do that calculation, although we cannot bring this sum out of this directly, because this is finite linear. That is, we can only bring finite terms, number of terms out of this operator, which will be simply summation alpha I. Although we cannot bring this, I am warning again, we cannot bring this summation exactly out of this directly, but you should turn first this into limit and then finite sum, then you can bring, but the result is same, T of ei, which is same as summation of alpha I, while I goes from 1 to infinity, and T of I, you already know, T of I was simply defined by E of I plus 1, that is E of I plus 1. So let us see how our vector is, how our T is mapping this vector x. Let us see what is the image of x corresponding to T. So this will simply get mapped if our vector is, we can simply write x as simply by alpha 1, alpha 2, alpha 3 in this sequence. But T of x was summation alpha I ei plus 1, which we can simply write as alpha 1 e2 plus alpha 2 e3 plus dash dash, which is simply 0 alpha 1 alpha 2 alpha 3 dash dash dash. This is known as right shift operator, that it simply shifts our sequence to the right by 1 unit or by 1 element. So let us try to compute its adjoint. First let us compute the inner product of Tx with the y. Let us take our element as x and y in our Hilbert space H and compute inner product of Tx with the y. So this will be simply inner product of Tx was our simply 0 alpha 1 alpha 2 alpha 3, and let us suppose y is represented by a sequence beta 1 beta 2 beta 1 beta 2 dash dash. So this inner product will be simply 0 times beta 1 conjugate plus alpha 1 beta 2 conjugate plus alpha 2 beta 3 conjugate plus dash dash dash. So like we separated the terms in the previous example, we will try to do same here. That is, we have the defined relation for the adjoint is simply, it should be same as inner product of with the T star y. From this we will try to extract the definition of T star y, which is same as, now we can write simply this inner product as inner product of alpha 1 alpha 2 alpha 3 with beta 2 beta 3 beta 4 dash dash dash. Hence, sorry, this is not inner product here, this is simply element here. We can write this inner product as beta 2 beta 3 beta 4 dash dash. Hence from this we will get the defining relation for T star y, because y was our beta 1 beta 2 beta 3. Hence from this, because this is simply our x, this should be simply as T star y. Hence T star y is simply defined by beta 2 beta 3 sorry t star y is simply defined by beta 2 beta 3 beta 4 dash dash, because y was our beta 1 beta 2 beta 3. Hence, corresponding to the right shift operator, its adjoint is simply defined by we can say it is a left operator. It is left operator. It simply shifts this back to the 0. It simply makes this 0 and shifts this left. Our t of x was simply shifts this element by this, but its conjugate simply shifts it back, the element back to the left. This is the adjoint operator for the right shift operator. Now let us try to define or give another example, but that operator is not bounded operator. We will try to construct another example, but that is a linear differential operator. We will try to construct it as we will try to define its adjoint, but this operator is not bounded. So boundedness is although not necessary for the adjointness. If operator is not bounded, then its corresponding conjugate will also be adjoint, will also be unbounded. Hence we have let us suppose the second order linear differential operator is defined by L of u, where u is some 2i differentiable function. It is simply defined by a d2u over dx square plus b du by dx plus c u. We will try to construct its adjoint, where a, b, and c are functions of x only, and the u and v are the elements of the some Hilbert space. Let us suppose they are from L2, where L2 is the Lebesgue integrable functions. This is a Hilbert space. So we will try to determine the adjoint operator of this linear operator. So by the defining relation for the adjoint, we should simply have inner product of Lu with some function, another function v, 2i differentiable, should be same as u L star v. And from this also we will simply write the definition of Lu with the v, and from that we will try to extract this definition L star of v. We will try to rewrite that inner product in terms of this, and from that we will extract the definition of L star v. So let us already how inner product on this space is defined. If we have two functions f1 and f2, their inner product is simply defined by integrating over certain region or interval f1 f2, where I am assuming these are real valued functions. Otherwise we have to take the conjugate of the another function from some interval a to b. So inner product of Lu with the v will be simply inner integral from, let me choose the limits to be ab, because already we are using small letters here. So it will be simply integral of v with the Lu dx. So we will try to compute simply this integral, and from that we will extract the definition of L star v. So let us try to first integrate this function a to b v Lu dx, which is simply by definition integral from a to b. v Lu is simply defined by a d2u over dx square plus b du by dx plus c dx, which is by the linear property of the integral, which is simply a to b v a d2u over dx square dx plus a to b bv du over dx plus integral cv dx. So we will first compute this integral, then this integral and this integral, and then from that we will try to extract the definition of adjoint. Yes. So let us first compute this first integral, that is integral of av du dx square dx from a to b. This is simply by parts, integration by parts, which is simply av u dash from a to b minus integral from a to b av dash u dash dx, which is simply av u dash a to b minus av dash u a to b plus a integral a to b av dash u dx. Av double dash should be here because we have to differentiate it twice. This is the first integral. Now let us calculate another integral, that was integral a to b bv du by dx, which is same as bv u from a to b minus integral a to b bv dash u dx. Now third integral we will try to write it as it is. Let us try to keep it as it is. Now the inner product of lu with v was simply integration of these three terms, which is simply, let me write that here, inner product of lu with the v was simply vlu dx, which is simply u dash av. We will collect all the terms, u av dash plus u bv from ab plus integral from a to b of u av double dash minus bv dash plus cv dx. Now this inner product should be same as inner product of u with the L star v, that is it should be same as inner product of, by very definition it should be same as inner product of u with L star v. Now, like from the two previous examples, we try to extract the definition. When we will try to evaluate this inner product, but L star is not defined yet, but it should be same as this equality. It should be same equal to this thing. Hence, from this integral, it seems that it is same as integral from a to b. This is u function, and this should be same as L star of v. by very definition, by the inner product definition, this quantity should be same as L star V. On comparing, this should be same as L star V, because it is the inner product of U with some quantity, which should be same as inner product of U with L star V. Now on comparing, this quantity should be same as L star V. That is, L star V should be same as L star V should be same as AV double prime minus BV prime plus CV. You can do the calculation, you can differentiate this function twice and this once, and this, the result you are going to get, you can make this calculation. It is very easy, differentiating simply. You will simply get d2 v over dx square plus twice a dash minus b dv by dx plus a double dash minus b dash plus c of v. Hence L star is simply defined. Adjoint corresponding to the linear differential operator, second order linear differential operator, is simply a d2 dx square plus twice a dash minus b d by dx plus a dash minus b plus c. Hence this is the adjoint corresponding to linear differential operator, second order linear differential operator. Although we know that differential operator is not bounded, hence we were still able to calculate adjoint although it is not bounded, but linearity is necessary. It should be linear, otherwise we can't make calculations. This was all about properties of the Hilbert adjoint operators and some examples corresponding to it. Thank you. If you like this video, kindly subscribe my channel and share it to your relevant friends. Thanks.